So can you see my full presentation?
Yeah, looks good.
Okay, thank you. Thank you for the organizer to invite me. I'm going to talk about how free thiols regulate the interactions of a self and the self-assembly of the thiol-passivated metal nanoparticles. This work is a collaboration between our group at ChemCars, a group of undergraduate students that I supervise with Professor Stuart Rice at University of Chicago and Professor Mark Schlossman at University of Illinois, Chicago. So our experimental system is a 2D self-assembled assembly of gold nanoparticles at the air-water interface. Xiaoming Ling from Argonne National Lab and Josh Partner from University of Chicago offer us these spheres that they synthesize. So those core size of the nanoparticles about 5.2 nanometers. They're quite nicely narrowly distributed. They have dodecan thiols as a ligand, and they disperse in the organic solutions. When you spread on the surface of water, they form this nice nanometer thin monolayers. And these monolayers are really has exhibited really interesting elastic properties of at the surface of water. What we found that is we spread on the surface of water and we compressed sideways, the monolayer will change, buckled into multilayers, and it eventually will wrinkle, behave just like a piece of plastic sheet. And Professor Yeager's group from University of Chicago transferred those films onto a TM grid, so formed these freestanding films, and they measured the Young's modulus and find out they're quite high. It's on the gigapascal level, so it's even stronger than nylon and most of the plastic films. And in fact, they really can sustain high pressure during the test of solvent filtration. So our group have been interested in tuning this elastic properties of the films at the surface of water. And one of the knobs of tuning is the control the ligand concentration in the solution. So what we do to control the concentration is we determine the masses of the ligand and the gold in a very low thiol concentration solution using mass spectrometry. And then we back added the thiols to reach different concentration of the thiol in the solution. And we found that the monolayers of different ligand concentrations exhibit different buckling and wrinkling responses under compression. And when this concentration is about 30% of ligand masses, and you see the wrinkle, these films behaves more like a elastic, not elastic anymore, viscoelastic. So you compress the wrinkle and fold behavior just disappeared. And when we measured the Young's modulus, and we found also the Young's modulus peaked about this 20% of ligand mass percentage. And beyond that point, the Young's modulus drop quickly. So what have the thiols done to the gold nanoparticles to induce different elastic responses to films? Well, one theory is that because the gold and thiol bonds is a covalent bond, they're so strong, they will always stay on the gold once they are bounded. So in this picture, the gold nanoparticles is always fully ligated, and the free thiols are just the space fillers. However, this theory cannot explain that when the thiols are very low, you see those gold cores just stick together, meaning they're centered and they glue together. So if you have a fully ligated particles, they can't go that close to glue like this. So another theory is that the gold thiol bonds actually is not that strong. It's weak enough that the bonded thiols actually can fall off, forming this equilibrium exchange with the free thiols. And this process can be approximated by the Langmuir absorption kinetics. This actually was backed by the experimental measurement of people using various techniques to measure the equilibrium constant. So with this equation, the Langmuir absorption equation and the equilibrium constant, we're able to build the relationship between the equilibrium bounded thiols on the gold nanoparticle theta, which we called core ligand coverage, and the free thiol concentration. And this theta is also related to the bonded thiol concentration. So with the total of the C1 and C2, you can relate to the total thiol concentration, which we measured, was the core ligand coverage. So this relation tells us that as you remove the thiols, the gold just become more and more bold, and then eventually they can stick together. And I'd like to point out that this 30% that I mentioned before, above which the film seems to lose the elastic property, is about 90% coverage. So now we established that there are always free thiols in the solution. Then we ask, where have all the free thiols gone at the air-water interface? We like to know that how do the free thiols affect the self-assembly of the gold nanoparticles at the interface? And specifically, I'd like to know how the free thiols affect the structure of the ligand shells and then their environment, and how the free thiols affect the location, meaning the height of the gold nanoparticles on the surface of water. And we address those questions with MD simulation and X-ray liquid interface scattering. So let's first see what the MD simulation tells us. This is done by a very talented undergraduate student, Lindsay Novak, who is now a graduate student. This is her system is just a single nanoparticle with a different ligand coverage in the absence or presence of the free thiol, a monolayer of free thiols. Here, I'm only showing the result of the gold nanoparticle with the free thiols at the surface of water. So you can see that at the very low gold core ligand coverage, the thiol distribution at the bottom of the spheres and top of spheres are asymmetric. And this is thinner than the top. But as you move to a higher thiol concentration, the ligand distribution become more symmetric. And I would also like to point out that there is a dimple formed by the nanoparticle at the air-water interface, which is useful for our reflectivity fitting. Lindsay's simulation also shows something interesting about the structure of the free thiol layer at the interface, with and without the gold nanoparticles. Without the gold nanoparticles, the free thiols behave just like surfactants. They form uniform monolayers with the sulfur atoms anchored at the air-water interface, which X-ray data consistent with X-ray measurement. However, if you put a gold nanoparticles in there, you can see that the free thiols become disordered. And as you increase this coverage, the free thiols become more and more disordered. It's just you can see the sulfur atoms distributed all over the place, normal to the interface. And that shows that the interactions between the free thiols and the bonded thiols are quite strong. Now we'll look at the X-ray scattering data. This X-ray scattering measurement was done at our beamline at sector 15 and the APS. I will mention more at the end of my talk, which will describe our instrument and the upgrade plan. So use this instrument, we measure the X-ray reflectivity and the grazing incident X-ray diffraction. Han Sun, that was our postdoc, did the most of the experimental work and the data analysis. As here we show the typical Bragg rod diffraction pattern. It tells us that the nanoparticle form hexagonal order at the interface, and from the diffraction pattern, we can determine the center to center distance and the core size. The core size can also be directly obtained from TM image. So from there, we can deduce what we call edge to edge distance, which can be compared with a fully extended thiol length. So we can see that below the 94%, I'll bring this value up again and later also, below 94% of coverage, the spacing between the particles increase gradually. However, above this 94%, the distance increased quite fast. And that distance I already mentioned is corresponding to this 30% where we describe the elastic property of the films. So now we'll look at the fitting models for X-ray reflectivity. The model we use are illustrated in here. This is the top view for the gold nanoparticle, and this is the side view. So first, we introduce the size distribution in the fitting, and then we allow the free thiols, which represent as a green, to fill between the nanoparticles. And then third, we allow the nanoparticles to form a dimple at the interface as inspired by the MD simulation. And we introduce a height parameter, which is the bottom of the core to the surface of the water. And then we use a hexagon shape for the liquid shells instead of a spherical shape. And finally, we model the free thiol film as a liquid film with a variable thickness D. Of course, this is not the only model I've tried or PON have tried. There are 5 other models that we have tried from A to E. And as we can see here, that the model that I described it gives the best chi-square value. Actually, in the end, what stopped us from further modeling is the fact that the electron density contrast between the gold and the thiol is huge, so large that the data is just not sensitive to more sophisticated models anymore. So here we show the fitting results for the 9 sets of data, and the electron density profile for this fitting, for the gold nanoparticles on the top, and for the thiol film at the bottom, and this is the direction indicated the theta increasing for the data. So as you can see from the electron density, the nanoparticles moving away from the water as the theta increased, and the thiol film has become thicker and thicker. So from the fitting, we got this H parameter that indicate the height of the nanoparticle relative to the water surface. We can see that below this, again, with the 94% of the coverage, the nanoparticles sit basically right on top of the water. However, above this 94%, the nanoparticles moving away from the water and quite fast. So the blue dots here is the result from a simulation. Below the critical angle, there is offset between the X-ray data and the simulation. That could be explained by the fact that the interface, where you count the interface between the two methods, could be slightly different. However, the main difference is that above the critical angle, the MD simulation did not show any critical angle. But that could be due to the fact that in our simulation, the gold core was modeled as a spheres instead of a polyhedral gold crystal with flat facets. We know that these thiols are more ordered on the flat surfaces. Nevertheless, I'm quite amazed the agreement that these two methods could achieve for this qualitative pictures, even given the limitation that the simulation is just one spheres, and in the scattering, the gold scattering just so domineering. So now I'm going to quickly, briefly describe this X-ray reflectivity fitting engine that we use for all the reflectivity fitting shown previously. I know that on Thursday, Renaud Barreau is going to talk about this software called Analyzer that he and Wade developed. So you will get more details from him, and you can pepper him with more expert questions. But here I'll just quickly say that for the users, they will construct a model of electron density profile with few slabs and interfacial roughness, and then user will fit the model at this level. The interfacial roughness is included with error functions. Many alternative functions are available in addition to the slab model. So behind the scene, the calculation engine operates on the user selected model for electron density profile, and the electron density profiles are sliced into hundreds of thin uniform layers with equal thickness. And the reflectivities are calculated exactly for many layers by original Parrot algorithm, and it worked with for arbitrary models also. And finally, the difficulty with Nova crochet approximation and bypassed. So in summary, the MD simulations and X-ray scatterings both shown that in the presence of a free thiols, bonded the thiols on the gold cores, and the free thiols interdigitate and produce a symmetrical ligand shell. And in addition, the X-ray scattering shows that above a critical value of theta about 94%, the gold cores rise above the water surface quickly, and the gold spacing increase also very quickly. And that 94% happened to be corresponding to the point above which that the gold film seems to lose elasticity. So for the next two slides, oh yes, sorry, the conclusion is that free thiols regulate the organization of bounded thiols on the core and the interactions of the nanoparticles with their surroundings. So I have two slides here just describing the liquid interface scattering at our beamline sector 15 advanced photon source. So our beamline is funded by US National Science Foundation. We run 3 techniques in tandem. The small molecule crystallography in the BHUTCH and the DHUTCH, and the liquid interface scattering in the DHUTCH, and the anomalous small angle scattering also in the DHUTCH. The energy tunable ranges from 5 to 70 keV. And here we show the our liquid interface scattering instrument that was built in 2002. It's a single crystal steering geometry. It has a quite large Q range. QZ can reach to 4, although we never even reached above 2 because there's just no scattering from the samples. And the in-plane, this arm can rotate at 90 degrees. And this instrument has a high spatial resolution. And we have used the Pallades detector 200 for reflectivity, for GID, diffuse scattering, all the same detectors. And we use Pallades 1M cadmium telluride for high energy above 20 and 30 keV. We also have a vortex detector, it's the energy dispersive detector for X-ray fluorescence measurement. So because of the strong demand from our user community for more beam time and new techniques, NSF recently funded us to construct a second beamline that will be up and running hopefully in 4 years. The 2 beamline optics are shown the following. The straight line, which is the existing line, will be upgraded with a new double crystal monochromators. So energy ranges still can go between 5 and 70 keV. And we also added a 2 pairs of multi-layer crystal here, multi-layers as our monochromator. So that's just for enhance the photons at 20 keV and 30 keV. We're going to have a new bent flat mirrors that will be much better than what we have currently. And we also will have CRL, which has a 1D and 2D focusing lenses. For the second beamline, the first crystal is the straight line, and the beam sidekick it into the second crystal. This second crystal will travel 5 meters to cover energy range between 3.5 to 31 keV. And this line doesn't have focusing mirror, we just use CRL, also 1D and 2D CRLs for focusing. So that way, the liquid interface at the CHUTCH is still existing. In addition, we add another instrument. This one is the double crystal steering the beam for the liquid interface scattering measured. And this is the kind of geometry that Bridget had pioneered, and Tom also worked on this geometry. It's what I call a Tesla of the spectrometer. And with this 2 beamlines, we can double the capacity to span the liquid interface science user community. And this upgraded also tied to the APS upgrade, which will be up and running in 2024. And with this upgrade, we'll have a new opportunities for liquid interface community. For example, we can scatter from solid liquid interfaces. This is the new diffractometer will do. And for the smaller beam, we can work on smaller samples, and we can scan the inhomogeneity and the defects at that interface. And with a more coherent beam, we can possibly do some coherent imaging, and also with some more high energy flux that will enhance the scattering from buried liquid-liquid interface. So with that, I'll conclude my talk and acknowledge our team. That's the ChemiCars team. And we're very happy because this is right after we got the funding, both for the operations and for the second beam one. So I'm done.